Are you able to hear me?
Yep.
Okay. Good afternoon, ladies and gentlemen. My name is Garvin Boyle. I'm going to talk to you this afternoon about two proposed principles of a science of economics, biosymmetry and hierarchic symmetry. My slides are not advancing. There we go. Okay. I'll have to use the mouse. So let me introduce myself first. I'm not a physicist. I'm not an economist. I'm not an academic. I'm a retired project manager and a retired high school teacher. I've been building computer models for over 50 years, and I've been building agent-based models for over 30 years. And I've been studying sustainable economics models for about 10 years now since I retired. My presentation is going to have three segments. Introductory segment, then I'm going to talk briefly about each of the two proposed principles. Now, this presentation is inspired by the proposed methodology for developing science-based principles of a science of economics written by Zhi of Peking University. Her paper was published recently in the Research and Action Agenda for Ecological Economics. It came out just a few weeks ago. Now, economic systems are complex, adaptive, evolving systems. Our experience of economic activity is subjective and teleological, or purpose-driven. This means we wake up in the morning, we make plans for the day, we make some decisions, and then we spend the rest of the day trying to make those plans and decisions become reality. So all of modern economic theory is, perforce, biased by our subjective and teleological worldview. But science must strive to be objective or unbiased. There is a desperate need for economic theory to be redeveloped as an economic science based on scientific principles and practices. Now, Zhi proposes that a science of economics requires three kinds of principles. The first kind are the philosophical principles. These are the fundamental assumptions that underlie all scientific activity. Kitty Ferguson's list is very interesting in her book, The Fire in the Equations. An example of a philosophical principle is the laws of physics are invariant under translation in time. These kinds of principles are not really falsifiable, but they are certainly debatable. The third kind of principle that she proposes are called political principles. Now, these are really moral strictures, moral constraints that we decide to put on our economic activity. These bridge the gap between teleonomic science and teleological economic practice. So she says that social political principles must be consistent with philosophical and observational principles of science. The third kind of, examples can be found in the book on ecological economics by Farley and Daly. They suggest that we need to take these moral goals, sustainable scale, just distribution, efficient allocation. Then there's a fourth one that is proposed by Stanley in a paper that is being prepared for publication, resilience. Now, Professor Zhi argues that the observational principles of an economic science must be consistent with the laws of the other sciences, physics, thermodynamics, chemistry, biology, accepted bodies of knowledge, and also must be consistent with the framework of universal dynamics that I'm going to describe in a few minutes. I would argue that the laws of the sciences must be extended into economics via symmetries or sameness, and not by analogies or likeness. When you say A is like B, that's a fairly weak statement. Symmetry is when A is part of B. A has the same integral dynamic as B. A is constrained by B. These are much stronger statements than analogy. These kinds of observational principles, these are the ones that are usually associated with scientific methodologies of some kind, and usually observational principles are both falsifiable and debatable. In the practice of science, we seek out natural symmetries. A dynamic symmetry exists when there are aspects of a natural dynamic system that remain invariant while most or all other aspects are varying. Dynamic symmetries in nature are always associated with conservation laws. For example, in Newtonian mechanics, when Newton published his Principia in 1687, he said force equals mass times acceleration. If we do a little physics experiment now, we find that force is still equal to mass times acceleration. We express this by saying invariance when translated in time. And by Noether's theorem, we find that this assumption about being invariant when translated in time turns into the law of conservation of energy, a very fundamental law that no system is able to be in breach of. In the practice of engineering and economics, agreed upon standards of manufacture and/or construction create economic symmetries. Those aspects that remain unchanged are called the gauge of the symmetry. For example, the gauge of a railroad system is the distance between the rails. As the train runs along the track, if the rails change their distance, the train falls off the track. That's generally a bad thing. The gauge of an electrical copper wire is the diameter of the wire. As the current runs along the wire, if it comes to a narrow spot, the wire heats up and houses burn down. That's generally a bad thing. So we use symmetries to make the economy run more efficiently and more safely. Let's turn our attention briefly to the concept of the hierarchy of the sciences. The branches of scientific study can be organized into a nested hierarchy of increasing specificity and decreasing generality. Physical systems tend to be the most general. If you discover laws in physics, they apply to everything all the way up. Economic systems tend to be the least general, the most specific. The specific systems are nested within and are part of and are constrained by the more general systems. We also know that the branches of scientific study form a nested hierarchy of increasing complexity, that you have more intractable problems when you get into the social sciences and the economic sciences. Now, semantics, logic, and mathematics form a meta-system from which all laws of science spring. I arbitrarily choose to place this meta-system at the bottom in agreement with the arguments of Cohen and Stewart in their book, The Collapse of Chaos. Let me talk now about the principle of economic biosymmetry. Why do we need a principle of biosymmetry? Well, most sciences strive to be objective, that is unbiased, and an economic science must do the same. In contrast, mainstream economic theory is extremely anthropocentric, extremely subjective, and focused on money. So unfortunately, non-monetary ecological economic externalities are dismissed from most economic analyses as irrelevant. Such external costs are all paid for by third parties, that is, by elements of the biosphere external to the analysis. This has become an existential issue. Modern economic theory has become a distal cause of most of our global ecological crises that now threaten the future existence of our species. We need a Copernican-like shift. When Copernicus published his book in 1543, he started a paradigmatic shift that took about 140 years to reach its end when Newton finally published his Principia. We need that kind of a paradigmatic shift, but we need it quickly. We need to shift from the anthropocentric desires of neoclassical economics to the biosymmetric needs of some future economic science. And we need it in a hurry. So how do we do this? Well, I suggest we start by redefining the word economy. In fact, it's a retro definition. We need to go back to the definition that the classical economists used in the 18th and 19th century. It is not just a financial system. An economy is a livelihood system in which people meet their needs, such as food, clothes, shelter, family. A focus on finances misses most of the important stuff. Then I want to borrow a word from earth sciences, anthroposphere. This typically means scope of influence of human activity. Now I'm going to take that word apart into three parts. The biotic part is the flesh, bone, bloods of the people. That's the biological part of the anthroposphere. The technosphere is what we have built. The noosphere controls what we do, the instinctive and cognitive actions in society. Now, that describes something that's associated with the human phenotype. Every species has its own phenotype. So I've coined this word phenosphere to describe the same thing for each species. It has three components: a biotic component, a technosphere, and a noosphere. Once we have that standard word, then we can apply the principle. Each species has an economy associated with its phenosphere. The laws of economic science must be consistent from the perspective of all phenospheres. What insight does this give us? Well, all economies prosper at the expense of other economies. Transfers of wealth often involve extracting, reaping, catching, or otherwise harvesting wealth from another economy and appropriating it. The externalities of any one economy are paid for by organisms in other economies. It's a zero-sum game. We only have one planet, and it's only so big. If one economy expands, a number of other economies have to contract. Where would this fit in the hierarchy of sciences? Well, the concept of species first appears when you're talking about ecological systems, so it would start there, and it would apply to all nested systems that are found within ecological systems. This gives us a different perspective on our own economic activity. Under anthropocentrism, externalities become wealth transfers under biosymmetry. Ecosystem services become economic surpluses and deficits. Economic rents earned from abiotic resources become interspecies, international, and intergenerational debts. Marginal financial focus becomes a holistic biophysical focus. It also gives us a different perspective on our economic role in the world. Under anthropocentrism, this temporal cohort of the human species has claimed proprietary interest in the entirety of the earth. But under biosymmetry, as the dominant species and as the originators of this mess, we must assume trustee responsibilities for the entirety of the earth on behalf of all species and for both present and future generations. This has a direct impact on the way we see economics in the world. Anthropocentric economic theory would look like this. Now, those of you who might have some experience in project management will recognize some of these words. Scope of control, that's the mandate. Scope of interest, that's things that you have to take into consideration. Scope of influence, that's stuff that you change as a side effect, but you don't really care about. So the mandate of modern economic theory is economic activities, inputs, outputs, policies, institutions. The scope of interest is the stuff you can make money from, and the rest are the externalities that are discarded. Under biosymmetric economic science, this is flipped around. The mandate of an economic science would become the things that we find to be existential threats: biodiversity collapse, climate change, oceanic acidification, and so on. Okay, let me talk about the principle of hierarchic symmetry. Going back to the hierarchy of sciences, many laws or principles established at lower levels constrain the dynamics of all higher levels, including economics. In recent years, these multi-level dynamic laws have been called universal dynamics. Now, I've taken an interest in these just over the past few years. I've collected a list and I've put them together into a framework, trying to understand how they fit together. And it's a work in progress, but this is what it looks like at the moment. I'm going to describe essentially what's happening in each box, starting from the bottom up. Fluctuations and recursions. Low entropy microcomplexities emerge from time to time as low probability accidents of random fluctuations. So that's a creative process coming from the bottom. Conservation. Symmetries prevent the emergence of most microcomplexities, but also prevent the immediate subsidence of some microcomplexities that have emerged thereby establishing a temporary stable platform on which other microcomplexities can accidentally emerge. So we have a creative process pushing against a damping process. Then we've got evolutionary processes that select some microcomplexities for preservation, causing them to accumulate into complex structures. At the same time, we've got these entropy production processes continually degrading and disassembling complex low entropy structures. So again, we've got a creative process building up complexity and a destructive process tearing down complexity. Then at the side, we've got a variety of these other universal dynamics that add context and variety to this ongoing endless reinvention of complex, adaptive, evolving systems. So what does this have to do with economic science? Well, thermodynamics was discovered as a physical system at first, and there's no question that it applies completely, therefore, to all systems that are nested within the physical systems. But then we've got this thing, entropy, that was discovered at the same time as thermodynamics, but it's starting to become common understanding that entropy is a mathematical process that stands apart from thermodynamics. It works all through thermodynamics, but it also plays its own role, appearing here and there throughout the various kinds of systems in the hierarchy of systems. And then we've got these other, these evolutionary processes, generation, preservation, and accretion of complexities. But we've also got universal things that appear at different levels in the system. For example, carrying capacity only makes sense when you're talking about species within an ecosystem, but it applies to all systems above that. So, in all of this, we have an implicit research question. If the same dynamic is functional in some general systems at lower levels, and if these are nested systems, when can we assume that they also operate in the more specific nested systems contained in them at higher levels? Now, I'm going to make a quick diversion. I'm not going to explain this in great detail, but I do believe that every statistical physicist and every statistical chemist is an economist, and they just don't realize it. I'm taking this insight from a capital exchange model that I call Model I. This is a diagram of the density of macrostates where you've got entropy along the bottom and total wealth at the side. If we look at that from the top, that comes next. This is the diagram that J. Willard Gibbs published in 1873 with the available energy in there. You can see that, and the primitive surface. And he sent a copy of this diagram to James Clerk Maxwell, and that kicked off a discussion that eventually led to the development of statistical chemistry and statistical physics. Now, I've used PowerPoint to make a copy of that diagram. You see it's a reasonably good replication. Then we take this density diagram from the capital exchange model, and we take Gibbs diagram and put it over that, and we see that right here we have Gibbs free wealth. So I would argue that if you know anything about Gibbs free energy, you're already an economist because you've got a lot to say about economic behavior. I've also come across this particular equation when I was reading about Crookes' fluctuation theorem and an article by Jeremy England. I realized that this definition of change in entropy is actually compatible with my my agent-based model. So I took a cut through the middle of this diagram and plotted the data, and it looks like that. That brings me to the end of my presentation. Thank you very much for listening. Do we have time for a few questions?
Thank you very much.